How many tic-tac-toe final boards are there? A relatively simple case-by-case analysis, but prone to errors since I'm clumsy. That's why I asked GavMS to run a code to verify. From the 6 cases, I got 4 wrong before verification. Lol. The viewer can attempt to calculate them too. A player can put an X or O on the 3x3 board. This is a move. X moves first and alternates with O. Since a player needs at least 3 of their marks on the board, tic-tac-toe can only end after at least 5 moves. When one player can make a 3 in a row, we'll call it a final board. We divide the final boards into 6 cases. 5 cases corresponding to a winner after 5, 6, 7, 8, and 9 moves. Cases after 9 moves without a winner, it's called a tie. 5 moves, 3x and 2o on the board. For this to be a final board, the 3 x's must form a line. There are 8 possible lines, 3 horizontals, 3 verticals, and 2 diagonal, each leaving 9 to 3 equals 6 blank spaces to be used by the 2 O's, which we can place anywhere since they have no chance of forming a 3 in a row. There are 8 ways to choose the winning line, and for each of those, there are 6 choose 2 ways to choose the positions of the 2. This gives us 8 times 6 choose 2 equal 120 final boards for 5 moves. It only gets harder from here. 6 moves, 3x and 3o on the board. A victory on even-numbered moves can only be achieved by O. So here we decide where to put the line of 3 O's and the 3 x's after. We must be careful here. We can't let the 3 x's make a line since this implies they would have actually won the move before. We divide the line of O's into 2 cases. The 6 horizontals or verticals, and 2 diagonals. After placing the horizontal/vertical line of O's, there are 6 blank spaces remaining for the x's like before. However, not all of 6 choose 3 equals 20 ways of putting the x's are valid, as 2 of them place the x's on a line, which we want to avoid. Therefore, there are 6 times 6 choose 3 minus 2 equals 108 possible final boards with a horizontal or vertical winning line for O. For the diagonal winning lines of O, we can freely place the x's in any of the blank spaces remaining. This gives us 2 times 6 choose 3 equals 40 possible final boards. Combining both cases, we have a total of 108 plus 40 equals 148 final boards for 6 moves. 7 moves, 4x and 3o on the board. For 7 moves with x winning, let's first consider horizontal or vertical lines. After placing the line that consists of 3 x's, we have 6 blank spaces remaining to place the final x. Then, we have 5 remaining blank spaces for the 3 O's. We need to ensure the O's don't form a line. Since the extra x blocks one potential winning line for O, there's only one configuration of O's that would form a line. This gives us 6 times 6 times 5 choose 3 minus 1 equals 324 possible final boards with horizontal or vertical winning line. Diagonal winning lines for x are simpler. After placing an x diagonal, we can put the extra x anywhere on the 6 blank spaces, followed by the 3 O's in the remaining 5 blank spaces. This results in 2 times 6 times 5 choose 3 equals 120 final boards. Adding together the horizontal or vertical and diagonal cases, we have 324 plus 120 equals 444 final boards for 7 moves. 8 moves, 4x and 4o on the board. We again start with horizontal or vertical lines. After placing the winning line of O's in the extra O, we position a 4x. There are only 2 cases where 3 of the x's form a line, by putting the 3 x's on the empty lane and the remaining x on 1 O. Therefore, there are 6 times 6 times 5 choose 4 minus 2 equals 108 possible final boards. Diagonal winning lines for O are straightforward. The diagonals block any chance of x forming a line, so we can freely place the extra O in the 4 x's. This gives us 2 times 6 times 5 choose 4 equals 60 possible final boards. Combining both cases, we have 108 plus 60 equals 168 final boards for 8 moves. 9 moves with a winner, 5x and 4o on the board. The ultimate case. Placing 5 x's leaves exactly 4 blank spaces, automatically determining the placement of the O's. However, the problem with 5 x's is that it's possible to have 2 lines of 3 in a row at once. So our previously used case division might lead to overlaps. We will instead divide into 3 distinct cases. Horizontal line only. There's a horizontal line of x's, but no vertical or diagonal lines. Vertical line, no diagonal. There's a vertical line of x's, and a horizontal line is allowed, but no diagonal lines. Diagonal line, there's a diagonal line of x's, and horizontal/vertical lines are allowed. Case 1. Horizontal line only. We have 3 choices for the horizontal line of x's. To prevent the O's from winning, we must block the 2 remaining open lanes by placing one of the remaining x's in each. There are 3 to the power of 2 equals 9 ways to do this. However, 3 of these create a vertical line and 2 create a diagonal line, WIC. Therefore, there are 3 times 9 to 3 to 2 equals 12 valid configurations for this case. Case 2, vertical line, no diagonal. This case is almost identical to the first case, except we allow horizontal lines. We only need to exclude configurations with a diagonal line. Therefore, there are 3 times 9 to 2 equals 21 valid configurations for this case. Case 3, diagonal line. We have 2 choices for the diagonal line of x's. The remaining 2 x's can be placed anywhere in the 6 blank spaces. This gives us 2 times 6 choose 2 equals 30 configurations. However, this overcounts the configuration with 2 diagonal lines. Therefore, there are 30 to 1 equals 29 valid configurations for this case. In total, there are 12 plus 21 plus 29 equals 62 final boards with a winner after 9 moves. Ties. I counted manually and only got 12. GavMS ran a simulation and found 16. I missed the 4 cases where it looks suspicious. Therefore, there are 16 tie games. And the grand total is 958.
Yeah, we checked on the web and turns out someone really did this, so our answer is verified. The more popular scientist wins though. I posted the source code in GitHub if anyone wants to run the code. I coded using Python 3.10. Yeah, I definitely code them, not using GimA Pro or Cloud AI. Look at the cool readme though.